G'day, thanks for joining me. Let's continue on with our electrochem topic with today's lesson entitled The Nernst Equation, Concentration and Cell Potentials. We're going to investigate the relationship between concentration and cell potential qualitatively and quantitatively using what's called the Nernst equation. We've been looking at these reduction potentials, looking at what the value is telling us, both the sign and its magnitude. And then we were looking at how to determine cell potentials when you combine two of these half cells and make inferences about the feasibility of that reaction. So we're saying that the value of the reduction potential describes how easy the species is to reduce or oxidize. Where we have more positive values are easier to reduce, like these ones at the top. They are very good at gaining electrons. And the more negative, it's easier to oxidize, where we could also make inference about their ability as oxidizing agents and reducing agents. Something that's easy to reduce is going to be a stronger oxidizing agent. Something that is easier to oxidize is going to be a stronger reducing agent. Where to from here? We've been looking at these being measured under standard conditions. Let's remind ourselves of what that means. It means a temperature of 298 Kelvin. It means a concentration when we're dealing with aqueous solutions of 1 mole per decimeter cubed. We have a pressure of 1 atmosphere, and because we can't measure absolute individual electrode potentials, we measure them all relative to the standard hydrogen electrode, where our value here is implying if it's generating more or less voltage than the standard hydrogen electrode, because that is assigned an arbitrary value of 0 volts. The reason we were doing this is because of our redox equilibriums, the fact that we have an equilibrium system and we can shift the position of this equilibrium based on factors like temperature, concentration and pressure. And this is going to affect our reduction potential value, as we'll see today. So let's consider if we have non-standard conditions here. Temperature, concentration and pressure all affect the position of equilibrium. What happens if this equilibrium position moves? Well, let's remind ourselves what these values are telling us. A positive value tells us that we're favoring the products. It's implying that it wants to be in the reduced form, so the position of equilibrium is lying very much over to the right-hand side. So if we move that equilibrium further to the right, that value becomes more and more positive. Conversely, let's remind ourselves what a negative value is telling us. A negative value is telling us that it wants to remain in the oxidized form. It's very much favoring the backward reaction. So if we push that equilibrium further backwards, further to the left, it's going to become more negative. So we can change these reduction potentials when they're no longer under standard conditions. So let's think about that conceptually. I've got a little question here as I do. I've got a zinc redox equilibrium there with its associated reduction potential at standard conditions. Let's remind ourselves what reaction is feasible, as in the forward or the backwards. Let's remind ourselves what Le Chatelier's principle states about increase in our reactant concentration, and therefore what's going to happen to our reduction potential if we change that position of equilibrium. Pause if you want to have a think. Here are the answers. Let's look first at the sign. We have a negative value for our standard reduction potential. That tells us that it's in the reverse direction. So we're going to be having the backward reaction, which is going to be that feasible direction. And that makes sense. We know zinc is a more reactive metal, so it wants to exist as the ionic form. So we have a negative reduction potential, implying it doesn't want to be reduced, but we would have a positive oxidation potential. Remember, if we're flipping that direction, we're flipping the sign and making it an oxidation potential as opposed to a reduction potential. So the next question, what does Le Chatelier's principle state about increasing the concentration of the reactants? Well, your system at equilibrium, it wants to re-establish that equilibrium. So our equilibrium is going to shift to the right. If you increase the concentration of the reactants, the system's going to counteract that change, drive the forward reaction, and consequently decrease that concentration again. So now to the important part for today's lesson, what would happen to the value of the reduction potential if the concentration was increased? Well, it would no longer be at standard conditions, so we wouldn't have a plimsoll there. But we've just said that we're driving that forward reaction. We know that the forward reaction makes it more positive. So we would actually make that value, that reduction potential would become more positive. But crucially, we're no longer at standard conditions, so we would just designate it as an E. So let's investigate this a little bit more. Changing the concentration of a species in a redox equilibrium will change the electrode potential value. Consider where we have a cell as opposed to just one individual half cell. So I've got the classic zinc copper half cell, and we've got a cell potential. Recall that we get the cell potential by getting the reduction potential and adding the oxidation potential, where we have to flip the sign of that one that is being oxidized. All that we covered in the previous video, so that's there if you need a recap. Is this reaction feasible? First of all, have a think. What's our sign and our cell potential? It's a positive value. Very much yes, that is a feasible reaction. So now let's think in terms of what we've just been saying with Le Chatelier's principle and driving one of these forwards or backward reactions accordingly. What's going to happen to the value of our cell potential as we increase the amount of copper? Well, systems at equilibrium, if we increase the concentration of the copper, the system wants to drive the forward reaction to decrease it again, re-establish that equilibrium. So our value, if we're driving that forward reaction more, this value is going to become even more positive. So let's consider this experimentally. Let's say that we set up in the lab, we set up the galvanic cell with our zinc and our copper half cells, and we kept the zinc half cell under standard conditions, but we changed the concentration of the copper half cell, keeping the temperature constant. What would that look like? Well, it would look something like this. So what have I got here? I've got the cell potential that we're measuring. I've got the concentration of copper ions, which I've popped on a logarithmic scale just to squish everything nice and close together. And we end up with a very good looking linear relationship between the two of these. So each time we are doubling the concentration of our Cu2+, measuring the salt potential, and then graphing that against the logarithm of our concentration. When plotting experimental cell potential against log of copper 2+ ions, we get the classic Y equals mx plus C. That's going to be important in just a moment. The y-intercept will be the standard cell potential of the system, assuming standard temperature and pressure, as standard concentration is 1 mole per decimeter cubed. So what this is saying is that we can get the standard cell potential by running some experiments of one of these cells under non-standard conditions, because if our standard conditions is 1 mole per decimeter cubed, the logarithm of 1 is 0. So if we plot a bunch of points, we can extrapolate that using a trend line, and we can determine that when the log equals 0, we will have our standard cell potential, which is 1.1, give or take, always taken into account for a little bit of experimental error there, which these results are very much trying to simulate, thus not the perfect correlation on the trend line. Okay, let's introduce the Nernst equation, which goes a long way to explain the relationship we're observing over here. Formulated by German chemist Walter Nernst to determine the cell potential under non-standard conditions. So here's what it looks like. I'll pop it up, and it's a pretty fantastic looking equation that we have here. Let's go through each of these elements, right? So we'll talk both in terms of getting a cell potential under non-standard conditions, and we'll also talk about getting reduction potentials under non-standard conditions. But for now, I've just got it designated as E. So let's just talk in terms of reduction potential. So if we have our reduction potential under non-standard conditions, well, it's going to be the reduction cell under standard conditions, but then we've talked about the fact that we're going to increase it or decrease it. So we've got to change it by adding or subtracting something to it. You know, we've got all our different signs that can flip around and whatnot. So what have we got here? We know that the equilibrium is dependent on concentration, temperature, and pressure. So we got R, one we haven't seen for quite a while, the gas constant. T for temperature, we know that's going to affect the reduction potential under non-standard conditions. and we have Z, which is our number of electrons, and our F, which is our Faraday's constant, stuff we've been looking at in the previous videos. And then importantly, we have a natural logarithm, which is another kind of logarithm. You just got to find the button on the calculator more than anything. It's on there, trust me. And it's to do with the concentration of our oxidized and reduced species. All right, let's consider if we had this at 298 Kelvin. So we keep the temperature, we'll keep the pressure constant. Let's say the only thing that we're changing is the concentration that we have. That's the only thing that's affecting our reduction potential. So if we have 298 Kelvin, well, R's already a constant, F's already a constant, and there's some maths that can go on to convert between natural logs and log 10s, which are the ones we're more familiar with. So let's do all that behind the scenes, and we end up with an equation that looks like this. So this one, if we have 298 Kelvin, this is the one we can use. If the temperature's changing, then we have to use that one up there, and we can plug in the temperature accordingly. But let's have a talk about this one. So again, we've got the standard reduction potential. All of those constants we can simplify, also including that conversion between our two types of logs, to 0.059 divided by the number of electrons transferred times by the base 10 log of our oxidized species concentration divided by our reduced species concentration. All right, let's investigate this a little bit more before we apply it. Z there, Z is the number of electrons transferred, which is important in the redox. Let's consider the previous metal-ion system and the above equation as Y equals mx plus C. So this is the one that I popped up on a graph just before. I got it to give me an equation of the line, and I'm showing our redox reaction up there. So let's consider if we got Y equals mx plus C. So Y equals mx plus C, which I'm given the slope there, I'm given the y-intercept there. So let's consider what our Y is. Our Y is our cell potential. So that's our cell potential under non-standard conditions, is equal to our slope, which is 0.0292. X is the logarithm of copper ions, Cu2 plus, and then plus C, which is when the log is equal to 1, so that's our reduction potential under standard conditions. So that's our E plimsoll there. Let me rearrange this a little bit, and what we'll start to see is it's actually looking a lot like that. So E, I'm going to bring my standard cell potential up to the front there. Now these are cell potentials, so I should really specify cell there as opposed to a reduction potential. And then we're plussing that to 0.0292. Now we get that number and we divide by the number of electrons. How many electrons are we transferring in this redox? We are transferring 2 electrons. So if you multiply that number by 2, that's looking a lot like 0.059 divided by number of electrons. Again, you get that number divided by 2, you're going to end up with something very close to that, times by the logarithm of our Cu2 plus, which in this half cell, that's the oxidized species. Oxidized, concentration of the oxidized species there. Now we know that a solid metal, it's going to have a fixed concentration, so we don't have to include it. So you can see that we're deriving, based on this experimental relationship that we got there, we've got our Nernst equation. And just a reminder, this is when we're doing it under 298 Kelvin, which this experiment was being done under. Yeah, cool. All right, what next? We can use the Nernst equation to calculate either an electrode potential, E, or a cell potential, E cell. So I was very much doing that to do the E cell up here. If you're calculating a reduction potential, you can still get the cell potential, but you'll have to get the reduction potential under non-standard conditions, potentially the oxidation potential under non-standard conditions if you have it, and then you can add them together to get our cell potential. Let's see if we can put all of that together now. Question, a cell was constructed using 2 half cells at 298 Kelvin. We've got a bromine species and a manganese species, and we have some reduction potentials there. The bromine bromide half cell was kept at standard conditions, but our manganese ion half cell had concentrations of that, and that accordingly determine the electrode potential of our manganese half cell and the overall cell potential under these conditions. So why don't you pause and give it a crack? We got a couple of Nernst equations here, some info over there, a whole bunch of data here, and let's go through the answer now. So the first thing, look, we're at 298 Kelvin, so that's telling us we can use our simplified one. If it wasn't, we would have to use the one at the top there. And it's telling us this bromine-bromide half cell is at standard conditions. So we don't have to calculate it under non-standard conditions because our question tells us it's at standard conditions. So we're able to just use that reduction potential when we do calculate the cell potential. But what we've got to do is we've got to calculate the manganese half cell under these non-standard conditions. So let's do that using this Nernst equation. So our manganese 3+, manganese 2+ half cell. So our Nernst equation, we're getting a reduction potential here under non-standard conditions. It's going to be equal to the cell potential under standard conditions, the reduction potential, sorry, under standard conditions, plus 0.059 divided by the number of electrons transferred, times by the logarithm of the concentration of the oxidized species, divided by the concentration of the reduced species. Now, unlike our question that we had before, where we had the example, oh, don't look at that. Oh, I guess if you've already done it, you would have paused. I lost my train of thought. Unlike the previous example before, where we didn't include the reduced species because it was a solid, so it's got a fixed concentration, in this instance, our reduced species and our oxidized species both have concentrations, so we very much got to include them both. So now let's plug in some data that we have. So the standard reduction potential of the manganese half cell is plus 1.49 volts. So equals plus 1.49 volts plus 0.059 divided by how many electrons are being transferred. To go from a 3+ to a 2+, we have one electron being transferred, multiplied by the logarithm of the concentration of our oxidized species. So that's going to be the one that's the loss of electrons there, 0.5 divided by our reduced, which is 0.1. So 0.5 divided by 0.1. Let's do this like that. All right, we plug all of this in the calculator and we'll end up with a value for the non-standard conditions, which is 1.53 volts, plus 1.53 volts. Should include the sign there. Excellent, so what to from here? So we've now got to work out which half cell is going to be oxidized and which half cell is going to be reduced. So what did we have? We had, maybe I'll move this over here. We had a bromine, which was under standard conditions, so that would be a liquid, and that was gaining, well, we're writing the reduction potential, so let's write it out like this, to bromide ions, and that had a value, standard reduction potential of what? 1.07 volts there. Plus 1.07 volts. And now we've got our manganese half cell, Mn3+, aqueous, plus E- goes to Mn2+, aqueous, and that's got a non-standard reduction potential of 1.53 volts. So we're going to use our value there. Let's now think in terms of the value that we have for our reduction potentials and what this means for the oxidation and reduction. Well, our more positive one is the better oxidizing agent. So our more positive one here is our manganese half cell. So that's very much going to be reduced. That's going to be the oxidizing agent. Whereas our more negative one there is clearly the bromide. So that's going to be oxidized, and that's the better reducing agent. So to get our overall cell potential, we're going to get the reduction potential, and we're going to add that to the oxidation potential. So we said the species being reduced is our manganese down there. So we have 1.53 volts. I'm going to plus that to the oxidation potential, which is going to be the top one. But remember, this is a reduction potential. To get the oxidation potential, we've got to flip the sign because we're going in that reverse direction there. And that's going to give us a value of 0.46 volts, plus 0.46 volts. So there you go, we had our half cell under non-standard conditions, and then we use that to get the overall cell potential to give us our answers there. Brilliant. Just to finish up, we can look at calculating the standard reduction potential from the Nernst equation with some experimental data. So let's consider that. We talked about this earlier. Let's now link it to the Nernst equation. What would you have to do to the Nernst equation, if I use the simplified one here, to make, but you can think of the more complex one as well, to make E equal to E standard? Well, we got that there, and we're plussing something to that. Well, to make these two things equal each other, we've got to make sure that we're plussing nothing to it, so it remains unchanged. So essentially, we've got to make this whole variable there equal to 0, and we can do that by making the logarithm equal to 1, because log 1 is equal to 0, so multiply 0 to that, it's all going to equal 0. Log 1 equals 0, plug it in your calculator, double check it if you like, but that's very much the case. So that would remove our variable there, and that would make E equal to E plimsoll. And this is what we saw with that experimental result there and finding the y-intercept. When we have the logarithm equal to 0, so log 1, we end up with our standard, in this case the standard cell potential, or the standard reduction potential if you're looking at that. And that concludes our lesson on the Nernst equation, concentration and cell potential. What did we do? We deduced the reduction potential values, we deduced from the reduction potentials the relative reactivity of elements, compounds, and ions acting as oxidizing agents or reducing agents. We did a lot of that in the previous lesson as well. Constructed redox equations using the relevant half equations. I mean, we've been doing that all through this unit. Importantly for this lesson, we predicted qualitatively how the value of an electrode potential varies with the concentration of aqueous ions. So linking that to Le Chatelier's principle. And then quantitatively, to get some numbers to this, we used our Nernst equation. We've got our two versions, one of which is there. To predict quantitatively how the value of an electrode potential varies with the concentration of the aqueous ions. Some examples there. Brilliant. Tasks, as always. Pause if you like. Consolidate. One column at a time, bottom to the top. Brilliant. That concludes our lesson. I look forward to next time where we can conclude this whole unit on electrochemistry. All the best. Have a good one.